So here in this video, we're going to look at higher order derivatives of multivariate functions. What that means is what we've just looked, you would have looked at other videos on partial differentiation. So if f is a function of xy and we calculate the first derivative of this function, this would be your first derivative. Now that no one stops us from calculating the second derivative. So the second derivative of fx could be, for instance, partial 2f by x squared. Now that's the obvious one. What is other possible derivative of a second derivative of x would be, instead of differentiating the x derivative with respect to x again, one might be interested in differentiating the x derivative with respect to y. So basically that's what I mean. So it's the second derivative of the x that you already calculated. As second derivative of f with respect to x, now you differentiate it with respect to y. So you'll notice the order of these two here. Okay, one has to you need to think of the partial by partial x as an operator, and what it's doing is it's operating on f. Okay, so it comes and attacks this f, and this gives you the partial f by x. So when you now go and do a second derivative, it's basically what's happening is it's this situation. So that gives you your second derivative. But what if you're taking this time the y derivatives operator, and as it applies to the x derivative, so that gives you the second derivative, and in this order, where you can see it's coming from the left. So we first differentiate with respect to x, then we differentiate with respect to y. Now, of course, one can also calculate the second derivative of. I mean, if we started with f with respect to y, we could get the second derivative of f with respect to y as well, which is y squared. We could also get the second derivative of f with respect to y that we already have. Now we differentiate with respect to x. So you can see you get xy. Before you got yx, now you have xy. So let's look at this example as we calculate these different derivatives. So partial f by x would be just here cosine y plus yex, and the second derivative of f with respect to x is fx squared, and that's going to give you just here yex. Now if I wanted to calculate the y derivative of this would mean the partial 2f by yx. That means the y derivative of this one, which will give me minus sine y. Okay, minus sine y, and then plus ex. So that, you can see, gives those are a few of the derivatives. Let's look at some other ones as we continue in this example. We can calculate, of course, the y derivative of f, and the y derivative of x turns out to be minus x sine y plus ex. And if we can calculate, for instance, the second derivative with respect to y, and that is minus x cosine y and nothing else. Okay, and let's do the mixed partial derivative, which is the x derivative of fy, and that basically means the x derivative of this, which is going to give us minus sine y plus ex. Now I want you to notice something here. You'll notice that this and this are both the same. Now generally there is a theorem that states that if, it's sometimes referred to as Clairaut's theorem, so it basically states that if f and its partial derivatives fx, fy, fxy, and fyx are defined throughout some open region that containing a point AB, and are all continuous at AB, then fxy at AB is the same as fxy. So basically what it's trying to say is that fxy is equal to fyx if f is a continuous function and has continuous partial derivatives up to the second order. Okay. Now, of course, we can go higher, and we can calculate even higher derivatives. And I'll, for instance, mention here that if we went up to, say, for instance, the third derivative, so fx and then f2 x squared. By the way, we use this notation for the two sub x's here, f twice there, and we can go to the third derivative now, okay, which is this way. Now, of course, don't forget that we've already calculated. Now, when we go to the third derivative, keep in mind that third derivative means we have several permutations and combinations that may occur. What this means is the third possible derivatives could be is that you took the second derivative with respect to x and differentiated with respect to y. You can also look at the third derivative in such a way that you calculate it this way, okay? That's also a valid third derivative. So one has to look at all the possibilities of how, for instance, a third derivative could possibly be calculated. Are you looking at the first derivative with respect to x and then differentiate it again with respect to x? Or perhaps you're interested in differentiating it twice with respect to y after differentiating it once with respect to x. So all these different combinations are possible. Now, of course, we're here starting off with an x, so we can just as easily start with the y, and then, you know, we're looking at, for instance, y squared, and then we would move on to the third derivative. But one could go from here and say, well, as I did, no, I didn't do that before. So, for instance, one can calculate the third derivative of this with respect to x after taking the second derivative with respect to y. So that's an option as well. So this way you can see that several different types of third derivatives can be achieved. Here's one of them, here's another one, here's another one, here's another one, and yet another one over here. So this is something you need to keep in mind when you're calculating higher order derivatives. And now if you go to the fourth order derivative, there are even more combinations that might be possible. Now, you don't have to worry about it. It's the fact that we can calculate them doesn't mean that we have to. That depends on what is interesting and what is required. So we'll stop here for partial differentiation.